In the invisible light beyond what human eyes can see lies a revolution, a technology that doesn't just photograph the Earth, but dissects it. Every rock, every crop, every drop of water carries a unique spectral signature. And now across the globe, leading space agencies and unexpected challenges are in a race to read them all. Hyperspectral imaging, once the domain of classified military research, is fast becoming the next leap in Earth observation. From monitoring climate change and detecting illegal mining to early warnings for crop failures and mineral exploration beyond Earth, this is data at the atomic level, coming straight from orbit. While NASA pushes the boundaries of what's possible, countries like China, India, and even Pakistan's SUPARCO are developing their own platforms, igniting a hidden space race rooted not in rocketry, but in vision. This documentary uncovers the untold story of hyperspectral imaging, its classified past, its powerful present, and the quietly emerging players preparing to use it not just to watch the Earth, but to reshape its future. Long before it became a buzzword in satellite technology, the idea of hyperspectral imaging was born from a simple question. What if we could see beyond what the human eye can detect? For centuries, our perception of light was limited to the visible spectrum, what we call red, green, and blue. But scientists have long known that sunlight stretches far beyond this range, into infrared, ultraviolet, and many other invisible bands. Each material, from a leaf to a mineral to a cloud of gas, reflects and absorbs light differently across these bands. Like a fingerprint in light, the initial breakthroughs came not from space, but from spectroscopy, a branch of science emerging in the 19th century. When Joseph von Fraunhofer observed dark lines within sunlight passing through a prism, he didn't yet know he was glimpsing chemical signatures. But by the early 20th century, scientists were using spectral analysis to determine the composition of gases, stars, and even distant galaxies. During World War II, aerial reconnaissance picked up this thread. Military aircraft began using multispectral cameras to differentiate camouflage from natural backgrounds. These early systems captured just a few bands of light, but the idea was revolutionary. Analysts realized that even subtle spectral variations could signal hidden activity like disturbed soil or anomalous vegetation. The concept of collecting a high number of spectral bands simultaneously didn't materialize in earnest until the 1970s, with the rise of both remote sensing and space technology. One of the early pivotal projects was NASA's Landsat program. Launched in 1972, Landsat-1 carried a multispectral scanner that laid the foundation for how we observe Earth from space today. Its ability to detect differences between vegetation types, urban surfaces, and water bodies was game-changing. But Landsat was still limited, capturing data in just 4 bands, visible and near-infrared. The ambition to collect dozens or even hundreds of bands with continuous spectral coverage became the central vision of hyperspectral imaging. The technology would allow scientists to detect things too subtle for any previous system, from early signs of crop disease to the mineral composition of exposed rock hundreds of kilometers below. In 1983, NASA launched the Airborne Imaging Spectrometer, AIS, essentially the first true hyperspectral instrument. Operating from a plane, it recorded data across hundreds of bands, offering unprecedented Earth science insights. Soon after, the AVIRIS, Airborne Visible Infrared Imaging Spectrometer, became the gold standard for airborne hyperspectral systems, still flown today by NASA's Jet Propulsion Laboratory. Parallel to these developments, classified military efforts were also underway. Defense agencies understood the value of seeing what others couldn't. Hyperspectral systems were capable of detecting chemical weapons, tracking concealed troop movements, even distinguishing man-made materials from natural terrain. Most of these programs remain behind a veil of secrecy to this day. Outside the US, other nations took notice. India's ISRO, China's CNSA, and even Pakistan's SUPARCO started investing modestly in spectral analysis and Earth observation, recognizing its dual-use potential, scientific and strategic. While they lacked the hardware at first, the theoretical groundwork was being laid. By the late 1990s, hyperspectral data started transitioning from airborne experiments to early orbital missions. CubeSats and small satellites made lower-cost experimentation possible, allowing universities and startups to enter the field. This democratization would prove essential in the decades to come. The seed was planted, from a prism in a 19th-century lab to sensors mounted on spy planes. Hyperspectral imaging had evolved into an idea chasing its destiny in orbit. The stage was now set for breakthroughs, rivalries, and a new kind of space race focused not on where we go, but how clearly we see. Hyperspectral imaging was no longer a theory, or even just a laboratory experiment. By the early 2000s, the first working systems capable of orbit-based hyperspectral data collection were being tested, and with them came a flood of breakthroughs that would permanently change how we observe Earth. The spark lit quietly, without headlines or ceremony, when scientific missions transitioned hyperspectral tech from aircraft to space-based platforms. It had been done before in pieces, fragmentary multispectral snapshots from early satellites, but true hyperspectral imaging from orbit, collecting hundreds of narrow spectral bands, demanded a brand new set of capabilities: ultra-precise optics, stable platforms, high-throughput data transmission, and serious onboard processing. In November 2000, NASA launched EO-1, the Earth Observing 1 satellite. Alongside more well-established sensors like ALI, it carried a powerful experimental instrument, Hyperion. Hyperion was the first civilian hyperspectral imager in space, capable of collecting data across 220 spectral bands. It could distinguish between grass and wheat, dry soil and wet sand, healthy coral and bleached reef, all at roughly 30-meter spatial resolution. And it proved something critical: hyperspectral imaging could work from orbit. Though originally designed for a one-year mission, EO-1 and Hyperion tremendously overperformed, continuing for over a decade. Researchers around the world accessed the data freely, marking the beginning of a democratized hyperspectral era. Mineral mapping, environmental monitoring, agricultural health studies, even archaeological exploration, all entered a new phase of precision. EO-1's success signaled to other space agencies this wasn't a gimmick. It was the future. Parallel to these civilian breakthroughs, classified programs were also making quiet strides, especially in the United States, Russia, and China. In the US, defense labs had already been developing airborne platforms capable of detecting camouflaged equipment, chemical residues, and underground bunker activity using hyperspectral data. These programs, while largely hidden from public view, shaped the early development of hyperspectral algorithms, especially for target detection and object identification. It's believed that several classified U.S. satellites were already utilizing multispectral and limited hyperspectral capabilities as early as the late 1990s. These sensors were designed not for geology or agriculture, but for tactical advantage. Being able to tell the difference between a military vehicle and a rock, or spot disturbed Earth indicating a hidden IED, became a race of national security. China, meanwhile, began ramping up its space-based remote sensing during the same period. While its early hyperspectral efforts lagged behind NASA in terms of openness and quality, the CNSA, China National Space Administration, began launching increasingly sophisticated Earth observation systems, and by the mid-2010s, its HJ-1A and HJ-1B satellites included hyperspectral-style sensors aimed at environmental applications. India's ISRO, known for cost-efficient innovation, started experimenting with hyperspectral capabilities in the 2010s through airborne missions and limited spaceborne payloads. In 2018, it launched HISIS, hyperspectral imaging satellite designed to serve agriculture, forestry, and coastal monitoring, collecting 55 spectral bands from visible through near-infrared. ISIS wasn't yet Hyperion's successor, but it proved India was serious about entering the spectral domain. Meanwhile, Pakistan's SUPARCO, historically slower in satellite development, began laying quiet groundwork. While SUPARCO has yet to launch a full-spectrum hyperspectral satellite, its programs increasingly collaborate with Chinese agencies, particularly via Pakistan Remote Sensing Satellite, PRSS-1, and the joint ecosystem around CPEC, China-Pakistan Economic Corridor. Analysts believe hyperspectral payloads, or access to Chinese data, could be integrated into Pakistan's future strategic space efforts within the decade, a significant milestone for a country traditionally on the periphery of advanced space, UDEC, while government agencies laid the groundwork. The first real disruption came from unexpected quarters, startups, companies like Planet, Satellogic, Headwall, and Orbital Sidekick began testing low-cost, low-orbit hyperspectral satellites designed for commercial customers. These new players could offer vineyard owners, mining companies, and megafarms access to real-time spectral analysis previously reserved for nation-states. Applications spanned oil spill detection, disease outbreaks, illegal deforestation, and urban pollution mapping, down to specific building blocks. In 2020, India's Pixel emerged as a serious contender, vowing to build the world's first commercial hyperspectral mega-constellation. With venture funding secured and a clear roadmap, Pixel and its peers represent a new movement, hyperspectral data not as national infrastructure, but as private intelligence platforms, rented by the hour. The key breakthroughs, both technical and institutional, were clear. Hyperspectral data could now be captured from orbit with useful resolution. Processing pipelines, once complex and expensive, became cloud-native and AI-powered. More nations began recognizing hyperspectral intelligence as a strategic asset. By the early 2020s, the world had quietly crossed a threshold. Hyperspectral imaging was no longer experimental. It was actionable, accessible, and accelerating. What began with a single sensor on a research satellite had now become a global race, not just for visibility, but for insight. As the 21st century accelerated into an era shaped by data, competition, and climate, hyperspectral imaging quietly ascended from a promising experiment into a global technology race. What began with one satellite, NASA's Hyperion, evolved into a multi-continent push to dominate spectral intelligence, with actors ranging from state agencies to private startups, all vying for control of the most detailed Earth observation data humanity has ever collected. This is the timeline of that ascent, structured not just by launch dates, but by political will, technical maturity, and the widening scope of applications. The launch of NASA's EO-1 with the Hyperion sensor in 2000 marked the world's first working hyperspectral satellite in orbit. Originally meant as a one-year testbed, EO-1 operated until 2017, completing thousands of scenes across environments, continents, and applications. During this time, researchers developed and refined spectral libraries, categorizing the unique signatures of different materials and land types, making interpretation faster and more automated. The Avarice instrument continued airborne missions, offering higher resolution data critical for algorithm development and calibration validation. Military involvement deepened, but largely in the shadows. Certain classified satellite reconnaissance programs are believed to have adopted hyperspectral sensors for advanced surveillance, although unconfirmed. Notably, during this decade, hyperspectral systems remained limited to research communities. The tools were powerful, but they required arcane knowledge and expensive computing capacity, making them inaccessible for broader civil or commercial use. This was the decade hyperspectral imaging scaled and diversified, with EO-1 winding down, NASA doubled down on airborne platforms like Virus NG, Next Generation, and Classic, offering data across 224 bands. The Jet Propulsion Laboratory JPL began working toward SBG, Surface Biology and Geology, a flagship hyperspectral satellite mission tied to climate and Earth systems. The HJ-1A and HJ-1B satellites, launched in 2008, provided multi- and limited hyperspectral capabilities tailored to environmental monitoring. In 2019, China launched Gaofen 5, a major leap in spectral resolution, capturing 330 spectral bands and aimed at pollution monitoring, mineral mapping, and resource classification. After years of airborne hyperspectral recruitment and academic research, ISRO launched HySys 2018, its first dedicated hyperspectral satellite. It sampled 55 spectral bands, mainly for land and coastal observation. Simultaneously, India's academia and defense sectors began developing hyperspectral algorithms, built with real-world data from international and airborne sources. The ENMAP, Environmental Mapping and Analysis Program, satellite, developed by Germany and launched under ESA in 2022, provided high-quality hyperspectral data with global coverage. The Copernicus Hyperspectral Imaging Mission for the Environment, CIME, aiming for a 2025 launch, is set to provide free, global hyperspectral imaging to users around the world, a potential game-changer in open-access Earth analytics. Although SUPARCO has not yet fielded a full hyperspectral satellite, it deepened ties with China through initiatives like PRSS-1 and CPEC's remote sensing collaborations. Access to Chinese data and infrastructure may serve as a springboard toward indigenous development of spectral payloads. Reports from Pakistani academic institutions indicate early-stage algorithm development and image processing research using open data sets from a virus and Hyperion, signaling future intent. This decade marks a sharp shift. Hyperspectral imaging left the lab and entered the marketplace. Pixel India announced launch plans for a 30-satellite hyperspectral constellation, aimed at daily Earth revisit cycles with FireMet resolution, focused on agriculture, pollution, emissions, and oil leak detection. Orbital Sidekick, USA, deployed its Aurora hyperspectral system on the International Space Station, followed closely by a string of CubeSat-class launches to build an orbital analytics platform. Satellogic, Argentina, and Headwall Photonics, USA, created high-spectral imaging payloads for commercial partnerships aimed at precision industries. From vineyards to gas pipelines, these players made hyperspectral data affordable, API accessible, and cloud-compatible, cutting down barriers for developers, researchers, and industry. As hyperspectral capabilities grew, so did their strategic significance. The US and allies began to classify certain bands or resolutions, especially those relevant to military asset detection or chemical traces. China incorporated hyperspectral imagery into the Belt and Road Initiative's geospatial backbone. Defense groups across India, Israel, and even Southeast Asia began funding research into hyperspectral surveillance, disaster response, and first strike detection. These developments firmly moved hyperspectral vision from academic exercise to national asset, akin to nuclear technology or cyber weapons, particularly when combined with AI-enhanced detection systems. We now live in a moment where hundreds of terabytes of hyperspectral data are generated each week across sectors. But raw data isn't the prize. Actionable insights are. The fusion of hyperspectral imaging with artificial intelligence, edge computing, cloud analytics, and multi-sensor fusion, LiDAR, SR thermal, has created a new kind of intelligence toolset. Governments and companies alike now use hyperspectral data for assessing crop yields a month before humans can, mapping mineral deposits remotely, reducing the need for hazardous field expeditions detecting oil spills or gas leaks, invisible to infrared monitoring, urban pollution and industrial compliance from space tracking climate change signals embedded in soil chemistry or glacier composition hyperspectral. Vision isn't just about seeing more colors. It's about seeing deeper truths, the chemical composition of life, the early tremors of climate collapse, and the hidden infrastructures of an accelerating world. Hyperspectral imaging has grown from a scientific curiosity to a tool of planetary awareness, and a core instrument in both Earth security and economic intelligence. But its most transformative chapter may still lie ahead, off Earth, where a new spectral arms race is brewing across the solar system. There was a time when hyperspectral imaging sat quietly at the edge of scientific curiosity, useful for academic experiments and niche government projects, but far from public consciousness. That time has ended. In just the past few years, hyperspectral imaging has undergone a paradigm shift, crossing the invisible threshold from specialized innovation to mainstream adoption. It's not just in orbit anymore. It's embedded in agriculture, industry, environment, and infrastructure. And at the heart of this transformation, a convergence of affordability, accessibility, and automation. What truly pushed hyperspectral into the mainstream wasn't just more satellites. It was turning spectral data into a utility. Traditional remote sensing required highly trained analysts and infrastructure-heavy processing. But powerful APIs, AI toolkits, and cloud-based pipelines offered by companies like Orbital Sidekick, Pixel, and SatSure changed that. Now, a non-specialist could subscribe to a hyperspectral alert platform and receive real-time insights, not terabytes of unreadable data. Farmers now get early disease warnings and nitrogen level assessments without ever seeing a spectrum chart. Mining companies locate ore-rich zones weeks before traditional surveys catch up. Municipalities track water contamination rapidly, cutting response time from days to hours. Just like GPS in the early 2000s, hyperspectral imaging has shifted from feature to foundation, part of the invisible algorithmic scaffolding of daily life. This revolution is not centralized, it's decentralized and collaborative in nature. NASA's HI-TS program supports wildfire detection, water vapor tracking, and methane leak monitoring across the United States. The European Space Agency's upcoming CHIME satellite aims to bring free, high-quality hyperspectral data to Earth scientists, accelerating climate research. Commercial players, Pixel, India, Zebra Imaging, USA, and Gumi Analytics, Pakistan, are pushing use cases into underdeveloped markets, monitoring illegal logging, precision farming for smallholders, and real-time infrastructure inspection. Surprisingly, developing countries are now embracing hyperspectral tech to perform with efficiency instead of scale. In parts of sub-Saharan Africa, hyperspectral services help map underground water sources, while in Southeast Asia, they're used for tracking coral reef health and illegal fishing patterns. What was once a billion-dollar satellite mission is now a startup service integrated via cloud subscription, accessible via smartphone. Climate preparedness, patterns of drought, soil degradation, and algae blooms are now tracked at the molecular level. NGOs can respond before crises escalate. Food security, from global supply chains to smallholder fields, crop health can now be monitored daily, reducing losses from disease and over-fertilization. Urban transparency, hyperspectral urban monitoring, is being used to regulate emissions, detect thermal leaks in buildings, and even monitor non-visible pollutants like invisible gases and fine particulates. Economic acceleration. Spectral intelligence is accelerating investments in critical minerals, renewable energy, and land leasing, shaving years off traditional discovery processes. In short, resource intelligence is becoming as vital as internet connectivity, and hyperspectral imaging is leading that charge. The societal shift mirrors what happened with electricity in the 20th century. Once unseen, now utterly essential, from silent satellites to actionable insights. Hyperspectral imaging has transcended the science lab and entered our homes, our markets, and our ecosystems, whether we know it or not. Hyperspectral imaging has officially entered its mature phase, and with maturity comes breadth, complexity, and new global stakes. Today, both public and private sectors are refining hyperspectral systems, diversifying them for specialized missions, and embedding them into the infrastructure of national economies, academic research, defense policy, and planetary stewardship. This is no longer a technology in waiting. It is a mission-critical capability that governments and corporations are doubling down on. And in doing so, the conversation has shifted from, can we collect this data, to how we should use it, ethically and equitably. In an increasingly unstable world, at the cutting edge of current capabilities, are satellites offering unprecedented temporal, spatial, and spectral resolution. Germany's NMAP 2022 is providing free, high-fidelity hyperspectral data to Earth science researchers across the globe, covering 230 bands from visible to shortwave infrared. It is one of the most advanced civilian hyperspectral platforms in orbit. Pixel, headquartered in India but operating globally, recently launched Anand and announced an ambitious 30-satellite constellation. Its goals are environmental diagnostics, precision agriculture, and mineral discovery, now offered as API-driven. Intelligence as a service to corporate clients. Japan's HISWI, aboard the ISS, and China's Gophen 5 series are proving their capacity to monitor industrial emissions, classify crops, and detect illegal mining from low Earth orbit, fueling environmental diplomacy and enforcement. Meanwhile, the European Space Agency's CHIME mission, slated for launch in the second half of the decade, will provide continuous hyperspectral coverage of Europe and beyond, publicly and freely accessible. In short, hyperspectral coverage is becoming global and increasingly civilian in orientation. Hyperspectral is no longer one-size-fits-all. New missions are being tailored for methane emission tracking to meet climate targets and detect violations, ocean color analysis, helping monitor coral bleaching, plankton blooms, and illegal waste dumping, urban thermal infrastructure imaging for energy efficiency and building audits, military-grade target identification, including landmine detection and camouflaged asset spotting. Even more surprising are non-orbital implementations. Medical hyperspectral imaging is being used in hospitals to detect tumors, wounded tissue, and surgical indicators invisible to the naked eye. Drone-mounted hyperspectral sensors are guiding precision reforestation and invasive species removal underground. Mapping systems use hyperspectral data fused with LiDAR to assist in archaeological, prospecting, and resource exploration. Today's hyperspectral platforms aren't just collecting data. They are adapting to mission-specific needs in both orbit and field-deployed environments. NASA is focused on climate surveillance, supporting SBIR programs that bring hyperspectral into wildfire modeling, polar ice monitoring, and ecological baselining. ISRO and Pixel are pushing for a dual strategy: sovereign data acquisition, HISIS, and expanding commercial hyperspectral services under one national umbrella, blending public good with private capital. SUPARCO, while not yet fielding dedicated hyperspectral satellites, continues to deepen cooperation with China's CNSA and academic collaborations, exploring data sharing agreements, payload development, and algorithmic pre-processing inside Pakistan for future use. China's CNSA and military sectors are investing in satellite swarm capability, creating redundant, resilient networks of hyperspectral sensors for civilian and defense observation, particularly along the Belt and Road corridor. Meanwhile, the private sector is no longer a junior partner. Black Sky, Planet, and Satellogic offer spectral analytics layered with real-time tasking, cloud delivery, and disaster response. Dashboards.ai-powered platforms now streamline hyperspectral data into structured insights within minutes, not days, enabling decisions in near real time. Yet, with new power come new complexities. Data overload is real. A single hyperspectral satellite can generate terabytes of data per day, putting pressure on ground stations, processing pipelines, and analysts. Privacy concerns have arisen as urban hyperspectral monitoring begins capturing detailed biosignatures, vegetation health, heat maps, even signs of occupancy or recent chemical activity. Spectral weaponization, using this tech for preemptive attack planning or subsurface mapping of strategic assets, has become a genuine concern in defense circles. Moreover, access inequality persists. While some nations build constellations and proprietary algorithms, others are locked out due to budget, bandwidth, or geopolitics, risking a new digital divide rooted not in internet access, but spectral access. Hyperspectral imaging today is no longer experimental, nor is it uniform. It is fragmented and focused, spread across space agencies, tech firms, universities, and startups, each pulling spectral vision in different directions, across domains from agriculture to warfare. What unites them is this: a shared belief that the invisible matters, that hidden within the light is knowledge about health, resources, danger, and opportunity, and now that knowledge is orbiting above us, every hour of every day. In the beginning, hyperspectral imaging was a scientific luxury, a data-rich, high-maintenance experiment understood by few and accessible to even fewer. But within a generation, it evolved into something far greater, a transformative tool now embedded in how we observe, understand, and manage Earth itself. Its true legacy lies not just in the pixels collected, but in the new paradigm it introduced that everything on Earth, living or non-living, natural or artificial, has a spectral identity, and that identity can be captured, interpreted, and acted upon. Before hyperspectral vision, Earth observation relied on the broad strokes of traditional imaging: colors, shadows, rough patterns. Hyperspectral imaging changed the canvas. It showed us that details invisible to all human senses, such as plant stress before it spreads, minerals beneath soil, or chemical imbalances in lakes, could be read from space with remarkable precision. In doing so, it unlocked entirely new domains: precision agriculture, allowing food systems to become more efficient and more sustainable; environmental accountability, enabling detection of pollution, deforestation, and emissions at source; disaster preparedness, with faster insights into floods, fires, and post-disaster contamination; resource intelligence, optimizing land use and mineral exploration without the ecological toll of ground disruption. Hyperspectral imaging also shaped the evolution of data culture itself, pushing forward cloud-native analytics, AI-assisted interpretation, and open data collaboration between governments, universities, and startups. What was once locked behind defense budgets is now being explored by students, farmers, and citizen scientists, but perhaps its greatest legacy is a more subtle one. It taught us to look beneath appearance, to seek truth in complexity, signatures beneath surface, and patterns beneath noise. And that mindset may prove to be hyperspectral tech's most important contribution, not just to Earth science, but to planetary thinking. Hyperspectral imaging has already redefined how we see Earth, but its future lies far beyond the treetops, cities, and oceans it monitors today. As geospatial tech advances and humanity ventures beyond the planetary edge, hyperspectral vision is poised to become far more than a tool. It's on its way to becoming an essential spacefaring sense. Agencies like NASA, ISRO, and ISRO are actively exploring hyperspectral instruments for lunar and Martian missions. From mapping ice deposits in moon craters to identifying hydrated minerals on Mars, future rovers and orbiters may be able to identify life-supporting elements without drilling a single hole. ESA's Lunar Polar Explorer and NASA's Artemis missions have proposed integrating spectral images to plan resource extraction for long-term habitation. The ultimate goal? Use hyperspectral vision as a kind of remote geology assistant, capable of prospecting water, oxygen-rich minerals, and construction materials on alien worlds. On Earth, the future points to strategic layering, constellations of small, hyperspectral satellites working alongside LiDAR, radar, and thermal imagery, creating multi-dimensional maps of Earth's surface and atmosphere in real time. Companies like Spire, Orbital Sidekick, and Pixel envision orbital swarms that update entire planetary datasets daily, not monthly. Imagine real-time detection of methane leaks in oil fields globally, or instant alerts about deforestation in the Amazon, delivered via API straight to a phone or drone. This opens the door to zero-delay geointelligence, AI-powered workflows that trigger supply chain responses, climate interventions, or even military deployments. Within the same hour, the spectral pattern is spotted in orbit. Hyperspectral technology is also miniaturizing and moving inward. In medicine, ultra-compact spectral images are being developed for real-time tissue diagnostics capable of identifying cancerous cells or oxygen-starved organs without incisions. In food security, handheld spectrometers may soon let consumers scan produce for ripeness, pesticide levels, or nutrient content in real time, making spectral literacy personal. In geology and archaeology, drone fleets equipped with hyperspectral vision could uncover buried ruins, track river migration over millennia, or map seismic fault lines, all without ever touching the soil. As the tech becomes more autonomous, airborne, and omnipresent, its future will hinge not just on innovation, but on ethics. Who owns hyperspectral data gathered over indigenous lands? Should countries be allowed to monitor industrial sites or agricultural yields outside their borders using orbital sensors? What are the implications of detecting activities invisible to all other forms of surveillance? Just as Google Earth reshaped conversations around privacy and sovereignty, hyperspectral Earth raises questions we are only beginning to understand. The global race for spectral dominance isn't stopping. It's accelerating into orbits, industries, and institutions still untouched. And with every new band of light we learn to interpret, we see more of what's truly happening around us. And within our reach, in the end, hyperspectral imaging may not just change how we see the world, it may decide what kind of world we get to see at all. From the grainy spectrometers of the 19th century to orbital constellations scanning Earth in hundreds of spectral bands, the journey of hyperspectral imaging is nothing short of extraordinary. Once reserved for secret labs and military payloads, it's now powering agriculture, climate action, disaster response, and interplanetary exploration. We've traveled through its forgotten routes, early airborne experiments, the rise of global space agencies, from SUPARCO to NASA, and the explosion of commercial innovation. And we've looked forward, toward a future where spectral vision sees not just through clouds or forests, but across oceans, industries, and even time itself. Hyperspectral imaging is no longer about light. It's about truth hidden in wavelengths, waiting to be revealed. And now, it's in everyone's hands. If you found this journey enlightening, do your part to elevate the conversation. Like this video, share it with curious minds, comment below. What surprised you most? Or what part of this race should we explore next? And of course, subscribe for more deep dive tech and history documentaries like this, because sometimes, to really see the future, you have to look beyond visible light.